Yes, thank you. Thanks, Srijit. Thanks for inviting me to talk to the students. Um, yeah. So, uh, good morning, everybody, and it's a pleasure for me to participate in this program to give this lecture. Let me start my share screen so you can see. And okay, uh, right. Yeah. So you said you can see the screen, right? Yeah. Okay. Srijit, stop me at any time, and
Sure,
I
sure.
may tell you go on, and you have to keep time and tell me also.
I will let you know.
Uh,
Okay.
so I've said computing as a science. Let me start with what it is not about. And so here's a quote: "Computer science is not really about computers, and it is not about computers in the same sense that physics is not really about particle accelerators, and biology is not about microscopes and petri dishes, and geometry isn't really about using surveying instruments." Even though the word geometry actually comes from measuring the earth. That's really the Greek origin, when they were actually interested in measuring distances. And geometry, of course, is used for that, but that's not the point of geometry, right? And I said not extra because you'll find all over people's quoting a statement, um, but that computer science is no more about computers than astronomy is about telescopes, and it's attributed to Dijkstra. So no, not at all. So this is so. This is about what computer science is not about, and the quote is also not from Dijkstra. It's actually from Hal Abelson in 1986, and poor Abelson is not as well known, and people usually attribute this to Dijkstra because this is the kind of thing Dijkstra used to say. Okay. So then, what is it really about? If it's not about this, what is it about, right? And here is another quote. This is slightly older English, as you can make out probably, I hope. It says, "We should explain before proceeding that it is not our object to consider this program with reference to the actual arrangement of the data on the variables of the engine, but simply as an abstract question of the nature and number of operations required to be performed during its complete solution." Does anyone want to guess who this is from? This is a quote, and it's a quote from somebody who says something about a program on a machine, and saying something about what it's about. And okay, so this is a quote from, why is this not mine? Yeah, Ada Augusta Byron King, Countess of Lovelace, writing in 1843. And she was programming Charles Babbage's analytical engine. And so long, and emphasis added, meaning I'm the one who's highlighted the required to be performed. She was not. So she says, you know, there is this engine. Remember, this engine is in her mind. Charles Babbage didn't build this engine. In fact, he didn't get money to build the engine. Okay, he designed the analytical engine. He designed the differential engine. And so Ada wrote a program, and a program for what? To solve a differential equation. Okay, not an easy program to write. Huh? She was writing a program to solve a differential equation on this engine. And she says, if you think it's about how the data is arranged on the variables of the engine, that's not our object. She says it's actually an abstract question of the nature and number of operations required to be performed during the solution of the problem. So she's giving an insight into problem solving where, so I would say, if you ask what is computer science really about, if it is not about, computers as like telescopes and whatever, what is it about? I think this is a beautiful quote for us to pay attention to. And she was a very colorful person. I don't know if you know, I mean, the world's first programmer was a woman, right? And in the 19th century, and she was working with Charles Babbage, and she was the daughter of Lord Byron. And those days, women didn't learn mathematics. It was not expected that women learn mathematics. They were disallowed. And how did she take to mathematics? Because she hated poetry. Because she hated Lord Byron, who was her father, because he treated her mother very badly. And, he was a womanizer and doing plenty of stuff, in the 19th century as lords could do. And so she hated her father and his poetry and therefore went to mathematics. And Babbage, you know, uh, took her on as a protege, and Babbage was an eccentric himself. And she learned mathematics from him and it's brilliant. And in 1996, late 90s, University of Manchester actually built the analytical engine and differential engine to Babbage's design. And they ran ADA's program and it worked. So beautiful programmer. Okay. So what I really want to say is this. In school, what is called computer science is mostly about computers and programming. Not really what computer science is about. And I think that's what I want us to think about in this time that we have got. It's a young discipline, so it's really easy to lose sight of what we ought to be really learning. And it's a fast moving and seductive. Computer science is very, very fast moving and seductive. So it's easy to let the fashions carry you, but that can leave you unprepared for the next fashion that's going to come along, right? So today's hot topic, if you run after, you know, what I, I don't know if you've heard the term computational thinking. I would say that's more a habit, a way of reasoning. In fact, if you get into the habit of computational thinking, that's useful not only for computer science education, which is what is your immediate goal, but also for whatever lifelong career you're going to have. This is what I would like to say. And that's really what I want to say, all I want to say today. Okay, so here is the, something doesn't move. Okay. So, well, Srijit, what is the degree called? In IITs, it's called Computer Science and Engineering, right? The BTech.
It's a BTech in
BTech is CSE.
Yeah, CSE.
Is it only CS or CSE?
It's CSE.
CSE, right. But you do call it computer science, right? You're hoping to, in fact, get a degree in computer science, right? And engineering, and both, right? But is computer science really a science? Yeah. I mean, you call it a science, but in fact, Europeans call it informatique, in French, informatic, in German, informatica, in Italian, and so on. Kybernetic in Russian. So they really call it information science. But still the question remains, how do you call it a science? See, you had all these subjects in school, right? What's special about science? What is distinct? What distinguishes science from other subjects? Can you tell me? One of you? Anybody, please?
It have no boundaries.
Poetry has no boundaries.
Science goes into the details of explaining things and why they happen.
Well, why? I doubt it. I mean, Newton's laws explain how things work. They don't tell you why things are that way. Right? You don't see why gravity should be there. No, I don't.
It's
I'm just,
continuously evolving. There is no.
But so is mathematics, I hope. Again, poetry. I would say poetry. Right? What is distinguishing characteristic of science? See, okay, I mean, this is a long argument, right? And Srijit doesn't give us that much time. So you have to think about this after all, right? If you think about it, there are many roads to truth, right? Humanity has many ways of approaching truth. Philosophy is about truth. Like I said, poetry, I find a very deep way of thinking about truth. But we don't, I mean, that's different, right? These are different ways, different pathways. In mathematics, what do you accept as true? Something that you can prove, right? Proof is the gold standard for truth in mathematics. You do not accept something because somebody says so. Unless it is proved, you do not accept. And the standard of proof, there are various things, deductive proof, etc., etc. What is the standard of truth in science? Do you prove things in science? You cannot prove things in science. The core idea is experimental verification. What you call true in science is something that is verified by experiment. That's why, and not you just do an experiment and say it works, you don't accept it. You do it repeatedly, right? Part of your pain that you go through in lab records and so on is repeated 10 times and take the average and so on, right? You do that. And it's not just that I do the experiment. Some Srijit does it in Goa, someone does it in Cincinnati, someone does it in Gumadipondi, someone does it in Somalia. And everywhere you get the same result, then you accept it as true. So the gold standard for truth is in poetry, intuition, words, style, whatever. Here it is experimental verification. If that is so, computer science mein kya? What experiment is there? Huh? What verification is there? I mean, how can you call it a science? I mean, right? Is there a role for experimentation in computer science at all? Right? Then how can we accept? Just one moment. Okay, computer is a machine, right? Does it even make sense to use a computer science, right? I mean, can we really have a machine science at all? I mean, that fan that is rotating above my head is a machine, but I've never heard of a fan science. This laptop I'm using, right? Well, I guess you have computer science at least, it's not laptop science, right? But I've never heard of a mic science or a microphone science. These are machines, right? So why computer science then? Is there some special reason for that? No. Okay, how about this? Let's think about it for a moment, right? Suppose we can have one. I mean, IIT has a department of mechanical engineering, no? But I've never, they don't call it machine science. I mean, you give a degree like computer science and engineering. The mechanical department doesn't give a degree saying machine science and engineering. They only call it mechanical engineering. It's only the computer crowd who arrogate themselves this right of calling it a science, right? Now, if you can have one, what would be the elements of a machine science? Let's just think a little bit about it. I have a proposal, and there is a machine that I like very much at home, which is a pressure cooker, right? Do you know what a pressure cooker is? I hope you do, right? You've seen it at home, right? In the kitchen. Pressure cooker, you put stuff in and put it on and it goes whistles and you get, cooked. Well, I have a proposal for a pressure cooker science, right? So I think it's a fine idea and I would like to suggest to you. In fact, I hope IIT will start a degree also in that. Okay, so what's a pressure cooker science? Well, here is a question. I don't know if any of you do any cooking. So let's see. Otherwise, I can always ask Srijit if you don't know. Right? Now, which takes longer to cook in a pressure cooker? Rice or dal?
Dal.
Dal. Dal takes longer to cook, right? Okay. What about potato or dal?
Potato.
Potato. Okay. I don't know what kind of potato that is. In my cooker, at least, I would explain. What about chicken?
Chicken.
Or potato? I mean, there must be some
Chicken.
non-vegetarians. Right? Goa, come on.
Potato.
Huh? Sorry? Someone
Chicken.
said
Chicken.
chicken takes now. But between chicken and dal, what is the ordering?
Chicken.
Chicken. Yeah. Okay. Yeah. This is what I would expect. Okay. And fish, no time at all. In fact, it is a crime to put the fish in a pressure cooker, I think. Yeah. But anyway, that's a different story. Right. So now the point is this. This is with your pressure cooker which you have at home. Let's say tomorrow some super duper technology comes, right? Srijit uses some quantum stuff and so on and comes up with one super cooker, right? Here is a quantum cooker, right? And it uses the latest quantum nano, whatever cooker, right? And in that, obviously, things will cook much faster. But which will take longer time in that cooker? Dal or rice?
Rice.
No, that's the point I'm trying to say.
Sir, it depends.
The constants will change, the time will change, but the ordering that chicken will take longer than dal, will take than rice, will remain because it's a property of the rice and dal and chicken. It's not a property of the cooker at all, right? Okay. What are the things, by the way, are there things that cannot be cooked in a pressure cooker? Let's not worry about just the things that do cook. Are there things that cannot be cooked in the pressure cooker? How about metal? Obviously, metal cannot be cooked in a cooker. Huh? That's why you put things in the bartan, right? You put things in a bartan and then put it inside the cooker, right? Why do you do that? Because that if that metal also starts getting cooked, you will have serious trouble. You won't even be able to eat that damn thing, right? Metal doesn't cook. In fact, metal doesn't cook in, forget pressure cooker. Tomorrow's super duper technology, quantum nano cooker will not cook your, because the kind of scales at which your dal and so on cook, energy scales involved are very, very different from cooking metal. Cooking meaning melting the metal, right? What about wood? Does wood cook?
No, sir.
No.
Can get cooked. It will take a very, very long time. What about your finger? Your finger will get cooked very fast, right? You even touch it, right? Oh, boom. Well, that's because what is the difference between things that get cooked and things that don't get cooked? Well, now we are getting into the heart of the matter. And that's, well, the answer is very simple. Anything that has water in it, right? Some water and carbon is what we are really interested in our foods. But water is in particular, what you call cooking rice is the process of converting that water into steam, and it escapes and it softens in the process. Molecular bonds are loosened, whatever. But look at what we have done in this 3 minutes. You use the pressure cooker to go look at the world out there. And you classify things out there in the world as those that cannot be cooked using my tool and those that can be cooked using my tool. And among those that can be cooked, you classify them further as this takes longer than this. You know, chicken, maybe rice is below, then potato, then dal, then chicken, whatever. And maybe, you know, pork or whatever, right? Red meat on top of white meat, and so on, right? So what you have done, classification, right? Classification is the beginning of science. There is a beautiful book by Scott Warren called Beginning Science. You know, we recommend it for elementary school children, but I hope even you will take a look at it. Warren tells you that science begins with classification. Science begins with classification as living, non-living, solid, liquid, gas. You know, bringing in terminology, it's called ontology in philosophy. It is by classifying things that science starts. And, you know, best of physics is by looking at energy scales. And of course, you go into classical and quantum and you can go deeper and deeper. But classification is at the heart of science. And that's really what we just did, right? So now what you're looking at and what you're studying is not a cooker at all. You're using the pressure cooker as a tool to go around. What are you actually studying? Things in the world, things that have water and things that don't have water. That's science, right? And you are classifying them and then giving, you know, and then in such a way, and this is at the heart of the matter, you're doing this classification in a technology independent fashion. This is very important to understand. That's what I mean by saying tomorrow some super duper technology can come. It may be microwave, infrared, but the classification will survive. That classification, that, is it technology independent is what you call the core of science. And this is really what we are doing here. Maybe I should draw a slide, not very good at this nonsense, but let me try. Okay, so what we did was this classification, right? So let me try. So what we did was take the universe of things, and this is not cookable. And these are all the things that can be cooked. and then you classify them. This is the easiest thing to cook. These are slightly harder. These are slightly harder, and so on. Right? But it's not very different to instead. Let me take. Okay, I don't have colors and so on. Instead of cook, let me erase this. And write. Oh, as I said, yeah. Okay. Let me use a slightly different word. The computer gives you a tool to classify things. Which things? Things in the world. Problems, the universe of problems, as those that are computable and non-computable. And among the ones you classify them, you say this is linear time, this is polynomial time, this is exponential time. I want to say that sorting things, sorting an elements take and log in time. And I say this in a technology independent fashion, right? That's at the heart, that's, makes it a science. You use a tool now, and the tool becomes a way by which you can look at the world. But what you're studying is not the tool. That's why you say it's no more about computers. It is about the things in the world, problems, the space of problems. There is another way to look at the pressure cooker, and that is to look at what happens inside the pressure cooker, right? How does the pressure cooker work, you ask? What are the principles behind it? Again, you describe the principles in a technology independent fashion. Even if you take the mechanism of the cooker, what do you say? Okay, there is, steam builds up, right? In an enclosed space, if, then what happens? That's a gas is formed, the gas is compressed, so pressure increases, and then that lifts the weight, that lets off steam, then it comes down. So you can write a differential equation to describe this. By the way, I've carried out all this stuff. I'm not just making empty claims. You can write an ordinary differential equation to describe this. You can talk about this motion. You can talk about this. That's another paradigm. You can go into the computer, instead of cooker, call it computer, right? You go into the computer and ask, what are the state changes that happen inside the machine? Can I describe these state changes? Can I describe its behavior for all time? Not as differential equation, perhaps, but in some technology independent fashion. Yes. And these is, I would say, and pretty much what happens in computer science as well, right? So the core that is technology independent, which is very important for whatever we are talking about, is essential for this. So what are the elements of a technology independent formulation of pressure cooker science? And then, well, but you don't have a pressure cooker science. If we start formulating our use of a tool, the computer, from these kind of one is an external way, use it as a tool to go around studying things in nature. Another is abstract descriptions of that. We find that here is a machine, it's really the mother of all machines in a very technical sense. But in a sense that you will actually learn to say that pretty much any machine formulation you can talk about can be simulated by this machine, by this abstract machine, right? And therefore you call it, okay, it's not any machine science, computer science, right? This is at least one narrative that I would like to have for you. So in some sense, it is both a new kind of science and a new kind of mathematics. And that is because it's a science of the artificial, right? And it's not a science of what exists in nature, but things that can be made, right? And a new kind of mathematics because it's a mathematical reasoning, but conscious in a particular way, asking specific kind of questions. That tool paradigm that I said, use it as a tool to go around classifying stuff. But what you are studying is the space of problems, is what is called the paradigm of algorithms and complexity. And the internal paradigm, where you look at the behavior and say, how is the behavior changing? And can I describe this behavior of change in an abstract mathematical formulation, but in a technology independent? This is the paradigm called logic and programming languages. And these are things that you will learn. Another two paradigms that you get when you start thinking about computers in this sense, one is as a computer as a problem solver, which is what I was talking about. Also computers as communicating systems. Because when did you last use your computer to solve any particular problem, right? But when you switch on your machine, your mobile, your smartphone, your laptop, anything, right? You use it for the internet, right? Today, the computer is a communication medium, right? It's a powerful medium. It's a medium with memory, but it's principally a communicator. Computer is communicator, right? That's another paradigm. So these are very important paradigms. And this is, I would say, I don't want to go more into these aspects because it will get too philosophical as to why you call it a science and a mathematics in this sense. Okay, here's a puzzle to get us thinking about why I said communication. Okay, it's a beautiful puzzle due to Martin Gardner. I have two distinct positive integers, x and y. X is smaller than y, such that, just to keep things simple, x plus y is actually less than 100. Okay, so these are small numbers. And there are two people. One is Miss Product and the other is Mr. Sum. And I go and tell Miss Product the value of x times y. I have picked the two numbers and I go and tell Mr. Sum the sum of x and y. Right? They don't know the actual numbers. They know the product and the sum respectively, and they know each other. Right? She knows that he knows the sum, and okay. And then the following conversation happens. She says, "I don't know what x and y are." Okay. Mr. Sum responds, "I knew that you didn't." And then she immediately says, "Oh, now I know x and y." He retorts saying, "So do I. Find x, y." And yeah, find x and y. This is the puzzle. As I said, Martin Gardner is full of beautiful puzzles. But I want you to, I mean, don't try to solve it right now. I assure you that you can solve it. I would expect at least half an hour of work involved. But I also tell you that, 2 to 3 hours of work and you will actually find it for sure. No problem. So it's not a deep problem by any means. It's a puzzle. But here is what's going on. What's the information content of the first communication? And she says, "I don't know what x and y are." Suppose I had told her the number 35, right? I tell you it's a product of two numbers and I tell you that it's 35. What are the numbers? If I tell you that the product is 35, what numbers are they?
7 and 5.
5 and 7.
5 and 7. It has to be, because it's a product of primes. That's it. There is a unique decomposition, right? So if both x and y were prime, she would immediately know them. So the first statement says at least one of them is a composite number. Beautiful, right? I mean, that's the information content of that communication. What about the second one? That's deadly, because now he says, "I knew that you didn't." Think about what exactly is the information communicated by that second statement. And the third is the beautiful inference there. When you put those two together, it implies the third. What the third means, you have to figure out. It's a lot of fun. And if you're the kind who can write a little computer program, I advise you to try to write a program searching through the possibilities, pairs x and y, and see what will work and what will not work. You'll have a lot of fun. I assure you it's not very difficult. But what is the content of the last one? That should be easy. It says that this pair xy is unique. That's really what it says, because obviously when she can know x and y, so can he. But the main point is that until then, there could be, she could know, but it could still leave the possibility that there are two pairs xy. The last one says, in fact, it's a unique pair xy. So for those who know a little bit of logic, you can try to write these statements in first order logic and try to, don't worry about it. That's not the intention of what I'm saying. My point is communication, information in communication, information leakage in communication, a whole lot of stuff out there. Inference, the process of inference that you are doing. This is not very different from what we call computation. There are deep theorems that assure you that these are actually the same things. But as a paradigm, as a way of thinking about it, anywhere you're looking at, here it's people communicating, you can think of agents communicating, programs, you will find very similar kind of reasoning. Okay, so let me quickly start telling you about what I mean by computational thinking. In a very influential paper in 2006, Janet Wing defined the characteristics of what the characteristics of computational thinking. Most important thing is decomposition of problems into sub-problems. Pattern recognition, right? Looking at things and recognizing patterns, representing them as data in particular ways, generalization or abstraction, and following and devising algorithms. Now, these are terms that, I mean, in general, mathematical thinking is also about this. I don't want to go too much into privileging these particular terms, but these are useful terms to follow. How can this be translated into, don't worry about curricular. What I mean is sort of things that you're going to see, but think of it as just systematic listing, counting, reasoning, looking at iterative patterns and processes, things that repeat again and again, and seeing patterns of that kind, and some kind of representation of data. I'll give examples of these and what is called discrete mathematical modeling. These are the elements of what we might call, computational thinking. Algorithms is at the heart of the whole business. Programming comes later. Underlying all this is digital literacy, right? What computers are about, what internet is about, etc., etc. So somehow the main thing is, when I say computational thinking, it's about moving away from find the answer to how do you know the answer, right? How do you know what you know? That's at the heart of thinking. For instance, this is for a primary school child, right? I say add, or middle school, I don't know what is the right level for this, add 204 and 78 for me. But before you do, tell me the order in which you will sum them. If you're going to do it in your head now, right? What is the order in which you will add these numbers?
First, we will add
We will add 2 and 7.
78 and
2.
2.
Correct.
And then
Why do
one
you
of
do that? Because for us as human beings, multiples of 10 are natural, right? We have 10 fingers, use the decimal, so natural. So in terms of what you've got, generally the point is this: what do you look for when deciding what is the best order for adding numbers in your head, right? So already you are looking at the input and saying, I order it in a way that is easy for me. That is computational thinking, right? It's not about doing BTech in computer science. You can start from primary school. You're in a conference hall or a wedding, let's say, with lots of people. Let's say anywhere between 100 and 150. Even COVID times, I think this is the size of a wedding. You're standing there. Now, lunch is to be served. Srijit comes in a hurry and says, hey, quickly tell me how many people there are. Now, how do you actually count how many there are? How do you know you have counted them all? How would you be able to verify whether your answer is correct? Right? I mean, confidently, will you be able to turn to Srijit and say, hey, I did the counting, it's 148 plus minus 4. With what degree of confidence can you say such things? Think about it. This is what I mean. This is a problem to think about for you in a situation, in a context, right? And it's not the answer that's important, but your ability to justify how you got there and verify all this is important. Here is a question. How many pairs of positive rationals sum up to 0.233? How do you answer this? 0.233 is a rational number. I've written in decimal. Okay, you think about it. Okay, this is the kind of thinking I want you to do. So here is when I say representation, what do I mean, right? There's a village in Goa where 61 families are Konkani speaking, 13 speak Marathi, 12 speak English or Portuguese, 8 are Tamilian, 5 are Malayali, and there is one lone Bengali family. How can we represent this information? You can write a table, right? It's a boring table, for sure, of course. But suppose I tell you that you can use one flag for each family, one color for Konkani, one color for Marathi, and so on. How would you represent it? Right? How would you depict it to yourself to communicate? Well, here is an attempt. I have actually, I have done it in such a way that it's actually 100. The numbers were done in such a way that it's 100, and the colors are exactly what I gave. But this is a completely useless representation. It's a faithful representation of the table, but completely useless because it doesn't give a clue as to relative numbers. What about this? I have put all the Konkani speaking together, right? This is a very good representation because it gives you a clue of how many there are. Quickly, you can even count how many there are. Here is another attempt. Okay. Now, these are all multiple representations of the same information. Now, of course, there is always a question about which representation you use for what purpose, right? In general, have you thought about visualization of information? If you have, you are into computational thinking. If you haven't, it's a good time to start. And the question to ask is, how much does representation matter? Now, I know that algebra is talked basically that. There's even a field called representation theory in algebra, right? But it's very important for computational thinking to ask such questions, to get into the habit. Like I told you, it's a habit of mind, right? And then to ask to what purpose? Because choosing between multiple representations for different purposes is at the heart of computational thinking. For instance, supposing I ask you, what is a polynomial? Is it an algebraic expression, in an expression language? Is it a function? Because it is a function. It's a polynomial function. Or is it an element in a ring? Abstract algebra. Point is, it's all these. And living with them all is important, right? And to be able to be receptive to multiple representations and get into the habit of asking which representation suits which purpose is the element of computational thinking. This is what I meant by data representation. Here is another picture for you. Here is a grid, a square grid, and I have joined some vertices to form a square. Here is one square. Here is another square. This is also a 4x4 square. Here is another, here is another square. Yeah. Now comes the question. Consider a 4x4 grid as above, right, with 16 points. What is the greatest number of counters you can place on the grid without 4 of them lying at the corners of a square? The way I placed counters was such that the 4 of them actually form a square. They are at the corners of a square. How many ways, how many counters can you place without there? How do you think about it? Yeah. So my point is, it's kind of combinatorial thinking, but it's also a certain way of thinking that is involved in this, which is at the heart of computation. Consider these shapes. What do you see is happening in these shapes? From the first to the second, what happened? Well, when I presented, somebody said, you rotated it by 90 degrees. Okay, that's one, maybe. Is there can you see some process that takes you from picture 1 to 2 to 3 to 4 to 5 to 6 to clearly the sequence goes on, right? What is very nice is one shape smaller and similar inside the shape that we started with. You start with a square, join the midpoints, new shape comes up, repeat the process and go on. Now, what is very interesting, you've got a process. The process is independent of what you started with. So maybe you don't start with the square at all. Now, take this whole thing that you've got, apply it to a different initial figure. In fact, you can start with any straight line shape, start with any, polygon. Can I do the same thing with concave polygons, or should I only think about convex polygons? Leave you to think about it. But you can make your own shapes. In fact, if you follow this, you're going to get beautiful screensavers, I assure you, right? With colors and so on, you can go to top. And in fact, what you get are fractals, as they call them, self-similar shapes. Little program, right? But the heart of the matter is iterative processes, patterns in iterative processes, and getting control over them, understanding them. For Tamilians, this is a very normal picture, especially during this time, December, January. Many South Indians know this. These are called columns. And these are drawn on the street, literally. I mean, if you walk out now in Chennai, you will see many, many columns, right? And they come in beautiful patterns. I especially like the bottom 3, which are called pulli columns, with dots and curves going all around them. And anybody who is from Chennai knows that if you go to the book fair in Chennai in January, you will get, literally about 500 books on columns, little booklets, all like 10 rupees, 20 rupees, these things. They're always published every year. Lots and lots and lots keep happening, right? These patterns. Now, if you start looking at it, you can explore this beautifully. I mean, you can ask how many closed curves are there in each of these, right? How do you classify them, right? Now, how would you describe, is there a language to describe this? Can you think of a process for drawing these? Think about these things. And I assure you, this is what computational thinking is about. So there are several habits of mind relevant to computational thinking. Systematic counting, listing, attention to iterative patterns and processes, exploring different methods of arranging, organizing, analyzing, transforming, and communicating information. Communicating information is not only about revealing information, it could also be about hiding information, right? Cryptography is about that. And so there's a whole lot of such stuff. Not settling for a solution to a problem, but asking what is the best solution, right? I mean, that's very important. You looking at multiple solutions and saying, this is better than the other. Being aware of the best may be the most cost effective or maybe the most equitable. There are various ways of posing that what is the best solution. Best solution to a problem, best solution to a social problem. Tomorrow vaccines are to be distributed. It's a huge procedural challenge for the country, right? You can give many, many procedures that solve the problem. Then you want to ask which is the optimal one. Which is the optimal one in what sense? Could be in the sense of efficiency of reaching. It could be in the sense of cost effectiveness. It could also be in the sense of equitability. What are the kind of activities that help to get into computational thinking? Well, packing things into boxes is a beautiful thing, right? Planning, searching for missing items, right? When you pack something, think about what if you need to find out something halfway through. Will you have to pull out the entire contents of the box to check, or is there a way? Can you pack in such a way that it's also easy to retrieve? Making codes, breaking codes. Many newspapers give a lot of cryptograms. Okay, so I don't want to go into examples of these. To say that there are a lot of examples from everyday life we can start thinking about, and these represent the kind of examples, the habits of thinking that I'm talking about. If you really want to understand what computing is about, as I said, in a foundational sense, it's important to ask the right questions. And what are the central questions to ask? When somebody is talking about computing, you want to ask what can be computed and how. What can be efficiently computed and how. What can be practically computed. The most efficient thing may not be the most practical one, right? You want to write a program in 2 days, huh? You don't want to take the most efficient thing and spend a huge amount of time doing complicated stuff, right? I want to do something in a practical way. How? What can be physically computed, right? Okay, are there limits, physical limits to many of the things that I'm saying? Maybe I'm talking about an asymptotic process that will converge, but is it physically feasible? What can be ethically computed? And I want to make this point because we forget that, finally what you are doing is a social activity, and there are ethics involved. And this is the age of big data. There's a beautiful book by Cathy O'Neill that I recommend to people. She calls it Weapons of Math Destruction, and how big data increases inequality and threatens democracy. That is the title of the book. And so increasingly algorithms are running our lives now. So it's a good question to also ask, where should computing agents be used? Why? Are there personal, social, and political contexts where the use of computing agents is actually undesirable? Who decides whether we should use them and how? What are the ethical dimensions of collective action, collective belief, that comes through social media, all these, right? And these are also questions to always keep in the back of one's mind as we learn, right? Because all science and technology ultimately impact society. And so these are questions. Let me end with the quote. Here's a note of caution from one of the eminent thinkers of computer science. This is Robin Milner in his ACM Turing Award lecture in 1992. He says, the trouble with computer science is that it's so applicable that it can be blamed for not doing immediately applicable research. He's talking to researchers, but even to students, this is very important. There is such an urgent demand for immediate applications that if you do work with long-term implications, you can be criticized. This is a great danger because computer science is so broad. There is so much computing happening, so much communication. We will all be lost without a basic theory. He said this in 1992 when internet didn't exist. You know, most of you were, for you, it's difficult to even think of what it was like in 1992, how computers looked at that time, right? So Milner talked about this long ago, and he said that when something is so prevalent, it's very important to understand the roots. And I want to say this to computer science students, principally because if you hitch on to platforms, you become obsolete when the platforms become obsolete, right? You know, this is a very fast changing thing, right? And I mean, in my own history of whatever 30 years of practice as a computer science researcher, I mean, I was in a software company for 1.5 years before I joined to do PhD in Tata Institute of Fundamental Research, and then in math science. In whatever I have seen, you know, fashions, you know, all kinds of fashions have come and gone. Right? What was the most fashionable thing in computer science? You know, 10 years, everything changes, right? But the new fashion will come for sure. C++ will go and D++ will come, right? If you hold on to these, you know, what
Hello, Jam.
strong foundations. So I would say that, you know, strong foundations is the heart of the whole business. So let me stop with that. And thank you very much for your.
So, thank you very much, Jam. Please, if you do have any questions, please feel free to ask Jam. He will
Yeah,
be
here is Robin
more than
Milner for
interested.
everybody who wants to see.
You're all free to ask questions. Jam will be more than interested in answering, talking to you.
Yeah.
Sir, what was the answer to that question?
The X and Y?
Yes,
Of course,
sir.
I'm not going to tell you, right? You're supposed to solve. I mean, puzzles, one doesn't give the answer. So you have to solve the thing, and you can write to me. I've given you my. I mean, if you're stuck, you can write to me and I will answer. Of course, I will. But only after you have tried and told me what you tried and what didn't work.
Yes, sir. What exactly did Robert Miller mean by a basic theory?
Ah, great question. So, yeah. So the basic theory that I don't know what he had in mind, right? But what he meant was, I expect that what he was talking about was what I call the technology independent formulation, the mathematical formulation, right? Something which is not about platforms, something which is not about, you know, where you look at computing. I would say in a mathematical sense, but you know, it's not the mathematics that's important there, right? It is the formulation, it is the thinking, it's a way of thinking that he's talking about, right? So I would put it in the kind of paradigms that I mentioned in terms of algorithm and complexity or logic and programming languages, these kind of formulations, but it can be different formulations. That's okay. But the core idea has to be something that's, you know, for instance, when I say that the sorting n elements from an ordered set can be done in n log n steps, or it requires n log n steps, that's going to hold in 2120, right? No problem. Right? God knows what the world will look like with all this global warming in 2370. But sorting will take n log n time. I mean, there is no problem with that, right? Because it's a formulation that has nothing to do with I mean, you can come up with quantum computers. It doesn't matter.
So we don't have a basic theory right now. Like
We do have, but it's theory in its infancy. I must say, you know, it's a very child theory, right?
so,
It
what's that
has a
theory, sir?
lot of growing up to do. It's not like mathematics, which has, you know, what, more than at least 2,500-year history. So you all have to build it. I mean, what we know is very little in that theory.
So computer science is more about information and how you handle it, and like.
Right, absolutely. how you, I mean, I would say how you represent it, how you visualize it, and even asking how much does representation matter, right? Not an easy question. Right? Because as I said, different representations are useful in for different purposes in different contexts. Figuring out which and when, that's part of computational thinking. Yeah. Yes.
Any more questions?
So what do you think about AI?
What is the question about AI? Yeah.
So,
What do you think about
so
AI?
what do you think about AI?
What do I think about it? Or what is,
Yes.
well, I mean, AI is there, right? So the question of, so when I kept saying computing agents, right? What did I mean by agents, right? You can think of it as programs, right? Computing programs. Now, these programs, the moment the program is, well, for instance, I talked about sorting an elements, right? I read a program to sort in elements. In some sense, if the program, the behavior of the program is entirely predicted, say this is what you should do and this is what it does, right? All the behavior is predicted. You don't call it an AI agent. An AI agent is something where you set up a framework and then you can only give the broad outline of the basis of what it does, and then it's supposed to learn. It's supposed to interact with the environment. It's supposed to learn and exhibit such learning to evolve in a sense, right? Such a thing is what is called AI agent. Now, if by doing that, do you exhibit intelligence? What is how much intelligence? These are very hard questions to answer. So there is no, there probably can be no accepted definition. So we take it. So one group of people take the human brain as the standard. So we try to, so that group says, okay, what we do is to build computer programs that demonstrate the kind of capabilities that the brain has, and so another group says, who cares whether it's like the brain or not, right? I don't particularly care. If, if I say a human being is very good at chess, I'll build a program that will be very good at chess. So it's showing intelligence. If you say human being is intelligent by participating in a conversation, remember the puzzle? That kind of conversation, right? No, I build programs that will, be able to participate in a conversation like that, and so on. So these are now what is something astonishing that we are finding is that a whole lot of this kind of behavior, you don't need to program too much in detail. A whole lot of the behavior can actually be learned from data. We'll have to see how again, the basic theory is still to be understood. And the other thing that we don't really understand is scale, right? Where when you have millions and millions of these going and interacting, taking decisions, decision making, even though, one component is only looking at some particular thing and taking decisions, when you put a huge network of these and they all start doing, we don't really know. So I would say that with respect to AI, we are barely scratching the surface right now. So what we understand is very little, but computer scientists are rash youngsters who go and build more and more. So we'll see as we build more and more, we'll understand more.
Sir, in case of AI, we provide the data. But what if we put a computer with a group of people which have a good, like same set of mind, like some people who know chess, and if we put a computer with it, so he will learn from them by playing with them. He will interacting with them. He will create his own data, and that may break the chains, the shackles between why AI cannot reach the height it is right now.
No. I mean, in terms of chess playing programs, the programs do what you are saying they should do. They actually do this. So in fact, there are many playing programs that learn by playing. That's no problem. They analyze chess masters' move. They actually play with chess master, grandmaster, and learn in the process. So this is eminently possible right now. And in fact, you know, the great Kasparov was beaten by IBM Deep Blue. So, and so today, I think chess playing programs can easily do. And in Go 19 by 19 was actually cracked by a computer a couple of years ago. And Go is a very, very difficult game. So as games of strategy go. But remember, these are dedicated special purpose computers. You know, its only job in life is to, you know, beat
do a particular job, but humans do many things at the same time. That I want to trying to say. We are making AI in a single path. What if we make a AI like a human?
That one would like to do, and I think that part is all waiting for Sajan Chaurasia to come and do, basically. Yeah. So right now, that's mainly because, see, the thing is this: chess playing or some game of strategy. You know, like Srijit said, I'm very much interested in game theory, right? Combinatorial games are easy to automate and program, algorithmize. What is much harder is the messy part of human beings, right? I mean, like vision. Um, Vision is not about cameras, right? I mean, vision is an act of cognition. Your eye is not acting like a, just a physical camera, because there are lots of, like, for instance, on this, my table right now where I'm lecturing, there are at least, 25 different things, right? But my mind records only a few of them, right? So you don't see everything in a scene, you only record a few. So that selection and forgetting, we don't know exactly how to do in vision, right? So our vision, smell, uh, these continuous gestures, like my hand is moving, all those are very messy things. So putting it together, which evolution has managed to do, is a thing that we find challenging. But on the other hand, like I said, this power of many, power of millions of components, millions of interacting agents, that's something else that humanity has never seen before. So we don't know. Anything else?
Sir, I wanted to ask, are like the systems of a computer similar to our brain? Like the processor, RAM, all those memory units and all them.
Right. I mean, in some sense, the brain is what has inspired all our models. That's true. But the kind of parallelism that the brain exhibits in neurons, right? I mean, we don't have anything even remotely close to that with the best technology that we have got so far. The kind of parallelism that we have in supercomputers is very impressive, but it's not even a fraction of the kind of parallelism that any animal, I mean, forget the human brain, any animal brain has. Because, literally millions of neurons are operating in parallel, and somehow they cohere together into that we don't understand very well. So concurrency is a huge challenge. Concurrency and parallelism and coordinating it. I think we are very, very far right now. But maybe there are some breakthroughs needed in understanding it. But yeah, I mean, so as I said, that's what is called strong AI. One group of people who work principally in, using AI as a way to understand the brain, and both ways. So, there is exciting collaborations going on between neuroscientists, cognitive scientists, people from psychology, people from neuroscience, people from computer science, physics, all coming together and doing research. Very exciting times in this.
Sir, while languages like C++ will ever get obsolete, it is able to perform all the tasks that it should do. Any new technology that can beat it, but C++ will still remain, I think.
Okay. I'm not really competent to answer that. Of course, I meant it as a joke to say C++ will go and D minus minus will come. Mainly because, as I said, in my own innings, I have seen several languages come and go. Now, I don't know enough about C++ to even throw galis at it. But what I do know is that for different purposes, right? If you're at the heart of operating systems and working at kernel level, the kind of programming languages that you want is very different from when you're manipulating things on the web. At different levels for web programming, for applications, for different things, different kind of uh, programming language structure is relevant. Yeah. So I don't know. I mean, in terms, I don't have any predictions on what will go obsolete. Yeah. But some will. That I'm sure of. I don't know which ones, but yeah.
Sir, these days there are like many innovations happening, like self-driving cars. Like today, Boston Dynamics they put up a new YouTube video of their robot dancing. It's like
Okay.
lot of cool stuff with, but these require lots of like computer chips and pro. So like. How much computing does like our human body require, like just to move around and just to like drive a car? Can like
Okay.
because like
No,
vehicles they have many processors, I think.
right. No, there are
Or
two different things that work in what you're saying, right? One is to, like you say, if you say, for a human being to drive a car, what are the muscles involved, what is the skeletal structure that is used, what is the neuronal structure used, everything, right? And can I come up with a robot which has the same capabilities and can drive a car? Another is to say, I don't give a damn about how the human being does it. I'm just going to develop a system that can drive the car, right? So the self-driving cars that you're talking about follow the latter policy. It doesn't go into the human thing at all, right? It doesn't look at the human dynamics and anatomy, etc. It's just about, here is a system, here is a control needed. I take it as a problem in a control systems angle and actually develop that. Use closed loop feedback techniques to do that, and that's what they do. On that, I think there is enormous progress. On the other one of coming up with a robotic structure that is able to replicate the human capabilities, like you look at that elbow and the hinge, right? These are great challenges. These are great challenges. If you talk to mechanical engineers, they'll tell you what the kind of difficulty that you've got in robotic arms and so on. So I think we are very far from that. So these are very different ways of looking at it. But yeah, and in terms of, by the way, I want to say one thing, right? When you say these days there are all kinds of innovations, there have always been innovations, right? In 1990, I can tell you there were great innovations from that time. I mean, from the technology of those times, they were coming up with really cool stuff. That's how you got the internet today, right? So there's always happening, and there will be more, no problem, right? So that's part of the reason why I'm saying that, these innovations will keep happening. They were happening. They will continue to happen. Some things will completely change your way of thinking. Mostly they won't, and that's the point. So if you hold on to patterns of thinking, that's going to. But a lot of new challenges come in the process.
So, like the car which is invented right now, which Google, I think Google is working on, is a automatic driving. So what they did is they build a AI, and from they don't give any experience to it. They just put that AI into work in a game called GTA 5, and it is itself learning from the rash driving that the players do in that game.
Yeah. Okay.
So that's the point I want to try to say is the way we are thinking about the AI route right now is nothing. We have to literally do something, like we have to treat AI like a human born baby. We have to put that AI into the real world with different groups, not in a particular group to learn a particular thing and to do a particular purpose. we
Right.
we need to give it a broad perspective
I
so that it can also do it research.
I completely agree with you. In fact, 1980. Forget about even before the kind of interactive systems that you're talking about. At that time, 1980, Simon Newell, Herbert Simon and Alan Newell, Simon and Newell published a book called General Problem Solving, right? So they started off in the 70s as the goal of artificial intelligence to become general problem solvers. No, okay. I mean, it's not about particular thing. The entire thing was about general problem solving, and they actually built a system called GPS, the general problem solver. Okay, so and Simon got the. By the way, Herbert Simon got the Nobel Prize in economics because he contributed to many areas of these things, and brilliant mind coming from very, very different perspectives. Now, so these ideas have been there all along. Now, when it comes to this idea that you don't develop AI for a particular purpose, intelligence is only about, so if you have talked to anybody in the 80s, they saw AI as developing general problem solving capabilities, general sensory capabilities like vision, speech processing, speech understanding, audio, all the senses that we talk about, right? And experience, exactly like you said, which is the process of learning, planning, learning. So these were considered the components of AI, right? Now, but in AI, as like I said, in the last 30 years that I have seen, there have been many fashions which have come and gone, mainly because there are beautiful ideas. Like general problem solving is a beautiful idea, but the tools that are there are simply too primitive compared to the sophistication of the general ideas. So sometimes you have beautiful ideas, but not enough tools to. Or like what is happening with machine learning right now, the tools are brilliant. I mean, they're running away with things. Theory is like desperate, trying to catch up and trying to figure out what the hell is going on, right? So I must say there are no clear answers to what you're saying, right? Coming up with general AI, let it, put it out there in the field. It interacts and learns through experience. One would like that very much, but I'm afraid the tools are. That's why I said they're waiting for Sajjan Chaurasia to come and do.
Thank you, sir.
Yeah.
Sir, I wanted to know, like we humans have our own consciousness and like a free space where we can think and like just yeah, think about any image or some word sound. So can we create the same thing for like a machine or like a computer, or they have they will think about anything they have in their memory at their own will, and not like a control system which is following process.
I mean, in fact, the answer to your question is in your question itself, if you think about it. Because if you ask, and this is really what Alan Turing started off with when he started off with computational knowledge. So if you ask, when you say, I sit and think, right? What exactly is going on, right? Now, certainly, clearly something is happening in the brain. Certain circuits fire, some neuronal activity take place. Now, question is, what kind of, is there a machine that describes how the neurons work? Unless you believe that there is some soul sitting there and activating that. If you believe that, okay, that's nothing much you can do because it's supernatural. We don't know how to. But if you say it's something natural, then you think of it as, okay, it's some physical thing, right? It's some machine that is acting when you're the processes of what you call thinking, right? So can I build a machine which is exactly the point, right? So I must say, if you proceed in that line of thought, right, it must be possible. Whatever you are saying, the answer must be yes, because we don't know any other way to do science, right? So it must be possible to build a machine that will do the same sort of things that you're talking about, what you call thinking, what you call ideas. I don't see why not. Mainly because, as I said, I don't see anything in principle that's against it. That's very different from actually being able to build a machine that does that. We are not there. But yes, the answer is yes. Question is how. Because that's mainly because we don't understand what's going on in the brain. Our understanding of the human brain, you said consciousness, right? It's pathetic with all the great, if you ask me what are the great questions of science, well, understanding, great questions of science for the 21st century. Somebody wrote the 10 questions. One of them will certainly be understand consciousness. What is consciousness? Right? Can you give any kind of mechanistic explanation? Use Newtonian mechanics, use quantum mechanics, whatever you have, but try to explain what is going on. Yeah, you will get your Nobel Prize, no problem. So my point is, it's not so much about AI versus artificial intelligence or natural stupidity or whatever it is. Okay. Problem is that we don't have a scientific understanding of these things at all. That's more the problem. You should read Roger Penrose's books, and Penrose has been talking a lot about these things. Yeah. Penrose got the Nobel Prize this year, among the physics Nobels. But he's also a great mathematician who's done all sorts of things. Written widely speculative things on computation. So you shouldn't, read it a bit critically, but you should listen to Penrose.
Okay, if there are no more questions, can thank Jam for this wonderful talk. Thank you, Jam.
Thank you. Thanks very much. Thanks. Okay.
Thanks. Thank
You
you.
can always write to me, as I said. Right?